So now I'm going to start a new portion of sequential circuit, that is a counter. Before going to the counter, two important topic have left, that is the preset and clear. The two inputs, basically one specific special inputs are provided to the flip-flop, that is a preset and clear. This small topic is essential for the rest of the syllabus, that is counter, register, etc. applications portion of flip-flop. So before going to the counter in details, I am going to clear the preset and clear, that is preset and clear. Basically, two type of inputs are there in generally given to the flip-flop, that is a synchronous input and asynchronous input. Asynchronous input and synchronous input. So asynchronous in place asynchronous input, we can say that for ASR, J, K, T, all inputs are generally synchronous input. These inputs are provided to the flip-flop, direct input. So these input are not direct input. The original input of the flip-flop, that is a ASR, J, K, T, D. These inputs are generally synchronous type of input, and some asynchronous input also provided to the flip-flop. That is that we can say that asynchronous input, or it can be say that direct input, or you can say this one is a overriding input. Overriding input. So why it is called overriding input, I am coming. So this basic I want to highlight this portion in this class. This is a right till now I have given means given idea about the ASRJKTD. But this asynchronous input or direct input, or you can say that the overriding input, are preset are clear, basically holds this property. So why it is necessary? First thing is that why we can study this preset and clear, and how this basically acts on the flip-flop. This is also more important, because without this preset and clear, some of the cases counter, registers, we can't construct these circuits, or basically combinational circuit of this counter and register we can't construct without this preset and clear, that is a direct input or overriding input. Overriding input basically override the decisions of the flip-flop. Preset functions like this, as preset gives a state to the flip-flop, that previous state, to remove the previous state of the flip-flop and override its own state. That preset provide a state to override the previous state of the flip-flop. I'm coming. And clears the memory of the flip-flop. Basically, we know that the flip-flop is acts as a memory element. So if we want to remove all memory elements, that to make the all memory element is 0, we can fire the clear. Clear clears the memory and gives the initial condition or 0 state of to the flip-flop. And preset is an input, one type of input that provide a fixed state to the flip-flop. And both are working as active low condition. Now I am going to draw the circuit of SR flip-flop so that it may be clear to you. So for this I need 4 NAND gate, 4 NAND gate SR flip-flop. So here 2 NAND gates also we need. This one is a QN, this one is a QN complement, and I am providing feedback. and this one is a S, this one is a R. S input, R input, this one is a clock provided here. Now this one is 4 NAND gates, G1, G2, G3 and G4. So if I am not giving any external input to this flip-flop, so this flip-flop follows the instructions, or flip-flop follows the truth table. Flip-flop functionality follows the truth table of SR flip-flop. Now from the outside, I am giving two input to this flip-flop. One input provided here, another input provided here. And for making this, I mention here one note, because this is a preset, this is a clear. I am abbreviated CR and PR, or you can abbreviate it CL or CR any. So what is the functionality of this preset? Preset is basically design with a predefined memory. Predefined memory, that means is active low. If I provide 0 in preset, so one of the input of this NAND gate is 0. So automatically this NAND gate output becomes 1. So wherever the input is providing, if we are providing 0, 1, 1, 0, 1, 1, 0, 0, any of the input we are providing in ASR, so after firing or after providing the 0 to preset, 0 input to the preset, that is basically active low, this output is overridden and output is presetted by 1. Qn presetted by 1. Is any output can Qn in any state, Qn may be 1, maybe 0, maybe anything. But whenever we are providing the preset, 0 input, 0 to the preset, then automatically the flip-flop gives 1 output, or flip-flop stores 1 to the Qn, or stores to the 1, or provide output Qn as 1. So this is the function of preset. And what is the function of clear? Clear is provided to clear the memory of flip-flop. So whatever the memory is possible, memory can be stored, flip-flop can store 0, flip-flop can store 1, any memory can be possible. But after giving 0 input to the clear, it automatically flip-flop is resetted and Qn to be 0. That is, if I provide 0 here, so automatically Qn complement is 1. So if Qn complement is 1, then Qn automatically is 0. So at means the relation I can write here, the preset of relation between Qn with preset or clear, say preset clear. Maybe both input can be connected in the flip-flop, or maybe single preset or clear can be connected with the flip-flop, or with a flip-flop without this preset and clear connection also possible. So as based on this state, I can write the truth table, like the functionality. I can tell you that the preset may be possible, that preset is 1, clear is 1. When we are providing clear 1, preset 1, that means the flip-flop is working as normal flip-flop. Normal flip-flop. So whenever this one is active low, so if we are providing high input, that is 1, 1, so this Qn is not under control of preset or clear. It follows the input provided to the S and R. So that is a flip-flop is working as a normal flip-flop. Now, if we provide a 0 to the preset and a clear to 1, so that means at that time flip-flop is working as a flip-flop is controlled by this preset, because preset is active low. So if we are providing low input to the preset, so at that time flip-flop is controlled by the preset. So automatically Qn should be 1. That preset is providing Qn should be 1. Now if it is possible that preset is 1, clear is 0. So when preset is 1 and clear is 0, at that time memory element is refreshed or removed, cleared from this flip-flop, and Qn should be 0. If possible that both the input are 0, clear and preset is 0, both are conflicting each other. Both are conflicting each other. Preset will direct the flip-flop Qn to be 1. Preset clear direct the flip-flop Qn should be 0. So these state generally not used. So this one is a relation between preset and clear with the Qn. And the block diagram of this Qn, the flip-flop with preset and clear can be provided down like this. ASR flip-flop. So here connection is a preset. This circle is provided due to this active low, and this one is this one Qn complement. Qn and Qn complement. This is a block diagram of SR flip-flop with preset and clear. So now I'm starting the counter. If you have any doubt, you can ask me. Do you have any doubt on that preset and clear? Am I audible?
Yes, sir.
Now I'm studying counter. So counter basically have some nature. That is first we can say that the nature of counter. So first and basic nature of counter is a sequential circuit. Counter is a sequential circuit. Next, what should I tell you about the counter? Next, counter is a basic element of counter is a flip-flop. So we can say that the flip-flops are essential. So flip-flops are essential element of counter. Next important point of counter is used for, it is used for counting pulses. Counting pulses. Next important point, I can say that if pulses may be generated by an event, so it can be say that the counter can be event counter. So if pulses are generated by an event, then it is called an event counter. event counter. And one another and the most important point I can say that the in number of flip-flops, in number of flip-flops can be used to count up to means maximum countable element 2 to the power n number of pulses. Better we can say that the maximum count can be possible 2 to the power n minus 1. I am coming with this. I'll tell you most probably within the next lecture. I can tell you the idea about this. Still, I am continuing. So now these 5 are the most important features of counter. In details of the counter, I am coming later on. So counter basically two types, mainly synchronous counter, asynchronous counter. So synchronous oblique asynchronous. But the counter in generally is 3 types. It may be possible synchronous, it may be possible asynchronous. Counter generally 3 types. First one is up counter. Second one is a down counter. And third one is the up down counter both. Up down count means up counter means the counter can be used to count the pulses 0, 1, 2, 3 increasing order. Down counter means it may be decreasing order 10, 9, 8, 7 this way. But up down counter, it can be the counter can count 0, 1, 2, 3, 4 or as well as counter can be possible to count the 10, 9, 8, 7. But a single time it is acts as a up counter or down counter. But the circuit, basically the circuit, logical circuit or combinational circuit controls whether the counter is used as a up counter or down counter. I'll tell you that, give you idea about the next classes, how up down counter is controlled. Basically, logic, we will define the logic that controls the up down property of the counter. Now, basically counter, type of counter, if we say that the type of counter, so type of counter is 2 types, synchronous counter, asynchronous counter. So I can the type of counter. So type of counter is 2 types, asynchronous and synchronous. Asynchronous, synchronous. Asynchronous counters generally can be said that the or otherwise name of the asynchronous counter is a ripple counter. I'll come to the why it is called ripple counter, why how the ripple counter works in the later on classes. We'll discuss on that. Ripple counter and the function, basic functionality I can can explain by using this one block diagram. That is, if I've taken 3 flip-flop to count to design a counter circuit. Here also I can take the 3 flip-flop for designing a counter circuit. So whenever I am going to design a asynchronous flip-flop, or anyone can want to design a asynchronous counter circuit. So asynchronous counter generally having clock pulse or clock is provided to the first flip-flop or the LSB. Clock is provided to the LSB, and after that clock is provided to the MSB, LSB. Clock is provided to the LSB, and after that MSB till MSB, this one is a LSB and this one is a MSB. So clock is provided to the LSB, and next flip flop getting clock from the output of the previous one. So this one is a QN. Q1, you can say that the flip flop 1, that's if it is a flip flop 1, so or flip flop 1, so Q1. So this Q1 gives the clock to the next flip flop. Again, if it is a FF2, so this output gives the clock to the next flip flop. So first is that a clock is provided for asynchronous counter. Clock is provided to the LSB, only single flip flop, and after that every steps clock flip flops of getting clock from the output of the previous flip flop. So output of the previous flip flop is given to the clock of the next flip flop. But in synchronous counter, flip flops are connected, or clocks are connected as in cascading condition. So parallel connection, all clocks are simultaneously provided to the all flip flop. So here this connection of the clock basically means controls is change the operational principle of the synchronous and asynchronous is different because of this clock connection. So I am coming what type of means difference is created in this clock. Generally, two type of flip flops are normally applied for designing a counter. Generally, we are using JK and T flip flop. JK and T flip flop. Sorry, JK and T flip flop is generally provided to for designing counters. So clock in case of asynchronous counter, clock pulse is not provided to the all flip flop. It is provided to the first flip flop. So clock pulse is not provided to the all flip flop. Keep it in mind that clock pulse is not provided to the all flip flop, and for synchronous clock pulse is provided to the every flip flop. So I am coming to the difference, or more difference are there of synchronous and asynchronous. I am coming with the differences. What type of differences this connection creates the differences basically. One minute. Asynchronous, synchronous. So first difference that for this asynchronous and synchronous. So as in case of asynchronous, flip flops are connected in such a way that output of first flip flop drives the clock of the next. So in case of synchronous, there is no connection. connection between output of the first flip-flop and clock of next of the next. Second point, all flip-flops are not clocked simultaneously. All flip-flops are not clocked simultaneously. Now, second of synchronous, in case of synchronous, all flip-flop are clocked simultaneously. Third point, circuit, this asynchronous counter circuit is simple. Still, if we increase the steps, but the circuit is simple. So can say that circuit is simple for more number of states. So 3 for synchronous counter. But synchronous counter circuit is not simple if we increase the number of states, because we need to connect the clock in individual flip-flop. So circuit becomes complex or complicated as the number of states increased. Number 4. So if the circuit is simple, so may say that the speed, but thing is that circuit is simple, still it can take the time. Why can take the time to run counting process? Because clock is propagated through the number of stages, because we have provided the clock to the first flip-flop, then first flip-flop output controls the second flip-flop output controls the third flip-flop. So by this way, circuit speed of the operation is slow. So you can say that the speed is slow as the clock is propagated through number of stages, and for synchronous counter we can say that the speed is high as the clock given at the same time. Clock is given at the same time. So delay of clock propagation of the clock is avoided in case of synchronous counter. And for this case, for this asynchronous counter, mainly what happened, whenever we are providing clock to the first flip-flop, So output at the time of first flip flop output controls the second flip flop. So whenever if we count if we want to count the total speed of the counter, then at that time delay of every flip flop is added with the clock. Propagation delay of every flip flop is added with the clock, so that the propagation of clock time propagation is high, so that the speed of the asynchronous counter is slow. So this is up to the difference of the asynchronous counter and synchronous counter. So now I'm coming. What is a flip flop basically? Flip flop is a flip flop. We can say that the 1-bit memory element. One bit memory element. And in counter, generally flip flops are used in the cascading format. So flip flops are connected. Say this one is a FF1, this one is a FF2, this one is a FF3. These all are connected in cascading format. So if I want to count some number, say that if we want to count a 3-bit number, if we want to count a 3-bit number. So how many states should be there for counting a 3-bit number? 3-bit number means A, B, C. So if we say that the ABC, so 3-bit number means 8 combinations are there. So 8 combinations are nothing but the 8 states are there. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So 8 states are there. Eight states. If I take the capital N is a number of states, capital N is the number of states, and small n can take that small n is the number of flip flops. So how many flip flops required to count the 8-bit number? Basically, the relation between the number of states and number of flip flop can be written as n equals to 2 to the power n. Or better, we can take the logarithm of this, or is better can say that we can express like this. So n is equals to 2 to the power n. So if I tell you that the n is a 3, so 3-bit number of states is a 8. Say 8 is equals to 2 to the power n. So if I apply logarithm, then we can say that the n equals to 3. So for 3-bit number counting, minimum 3 flip-flops should be necessary to count a 3-bit number. So 8 states, for 8 states counting, so a small n equals to 3. So how much maximum count can be possible in using this 3-bit number? So 3-bit number can count a 0, and this one is a 7. 0, 1, 2, 3, 4, 5, 6 and 7. So by using 3-bit number, we can count maximum number is 7. So can express this by this formula. So maximum count can be possible by using a 3-bit counter is 2 to the power n minus 1. So number of states, maximum count should be 2 to the power n minus 1. Number of states is n equals to 2 to the power n. N equals to 2 to the power n, and maximum count is 2 to the power n minus 1. if I can give you idea about the 2-bit counter, 2-bit counter. So for 2-bit counter, how many states are there? For 2-bit counting, states can be used like this: 0 0 0 1 1 0 1 1. So 4 states are normally have in 2-bit counter, and this force for this creating these 4 states, how many flip flop we should require for this? So 4 equals to 2 to the power n. So what is the value of this small n is 2. So maximum count is possible by using this 2-bit counter is the 2 to the power n minus 1, that is 4 minus 1 is 3. 4 minus 1 is 3. So by using this 2-bit counter, we can count maximum 0 to 3. We can count 0 to 3, or we can count 3 to 0. For up counter 0 to 3, for down counter 3 to 0, or for in this case also for up counter 0 to 7 or 7 to 0. But means we can apply this as up or down, any of the counter or both count. Now next is the most important portion of this expression of this counter. We can express the counter, or we can say that the counter is named by modulus. Generally, modulus or mod counter. So what is the mod or modulus counter? So generally the mod is called the number of states passed by the counter before going to its initial state is called the modulus or mod of the counter. So I can write the definition of modulus. So the number of states passed by the counter before going to its initial states is called modulus or mod counter, mod of the counter. So I'm in details I'm explaining this definition. The number of states. So initial state to the final state, if we count initial state to the final state. So number of states passed by the counter before going to its initial state. Say if I start from 0 to 7, 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, 7 to 0. So I am talking about 3-bit counter. 3-bit counter. So if for this 3-bit counter, number of states, so how much number of states we can cross? 1 2 3 4 5 6 7. After this 7, that is the last state is there. Last state is the 8. So after 7 we are coming to the initial state, that is 0. If I am talking about a up counter, that is in up or down any type of counter, the initial condition is 0. So initial condition I can count from the 0. So 0 to 1, 2, 3, 4, 5, 6, 7, and then 0. So 0 is the initial condition. So the number of states past the counter before going to its initial state called the modulus. So how much modulus for this counter we can say that is a mod 8 counter. Mod 8. Mod 8 counter. So mod 8 counter having 8 states, have 8 states, mod 8 counter. So can start from the mod 2 or mod 3 or mod 8. So mod 8 counter having 3-bit is called as a 3-bit counter, have 8 states, and by using mod 8 counter we can count maximum count. Max count possible for mod using mod 8 counter is a 7, and number of flip flops required is 3, and number of states is number of states is 8. So initial state, if we use for this mod 8 counter, generally 3 flip flops are used. So for this reference I can say that for mod 2 counter, how much flip flop we should require for designing a mod 2 counter is a 2 flip flops are required. How much states should be there? States, 4 states. And how much maximum count should be possible is the 3 count, 3 to 0 or 0 to 3. So by mod can be here I am giving you examples only for the mod the power of 2. So the mod 2, mod 4, mod 8, mod 4. This one is a mod 4. This one is a mod 4, not mod 2. Mod 4 counter. So mod 4 having 2 to the power 2 basically. Mod 4 having 2 to the n equals to capital N equals to 2 to the power 2, that is 4. That is 4. So in 4 number of states are required, and 2 is the number of flip flop. So I'm giving example here is 2 to the power n format, that is mod of 4, mod of 8, mod of 16. But it's possible that mod 10 also possible. Means it's not like that mods are only the power of 2. Mods can be 10, mods can be 9 and other also. That I will give you understand in the next class.